Okay, so I think my screen is visible. Cool. Can someone confirm if my screen is visible for them?
Yes, it's visible.
Okay, okay, sure. Okay, now I think some people are trying to join. So, yeah. Anyway, so yeah, welcome everyone. I am Sagnik Acharya. I am a PhD student at IISc Bangalore, and I am helping out as TA for this course in machine learning. So get started. I think now people are starting to join when we have just started this session. We'll do one thing. I think we'll wait for a couple minutes. If no one else joins, then we'll continue and stop accepting people. Okay, since no one else is joining, I'll start. Okay, so yeah, so I already introduced myself. So this is the second session for me. I'm sure there have been other sessions before this, and there will be other sessions taken by my fellow TAs as well this week. So for this week, I'll discuss week 3 content. So we'll just quickly go through some of the concepts, and I have a couple of sample problems, and we'll try to you know work through them together, and then we'll discuss any doubts which you guys might have. So yeah, let's start. So first of all, I want to discuss graph theory. So, in graphs are basically mathematical structures which are used to model pairwise relations between objects. So, graph is usually made up of vertices. So, all these so these are called vertices or nodes, you can call them, and they're connected by edges. So, the edges may or may not have these arrows. So, usually, if they have arrows, they are called directed graphs, and if they don't have, they are called undirected graph. And usually this edge, so this edge will have a weight associated with it. So we'll see what the use of this weight is when we discuss artificial neural networks. uh, and yeah, I discussed an undirected graph usually does not have these arrows, and a directed graph will have these arrows. And we call a graph connected if I can start on any random point in a graph and reach any other point. So for a moment, let's consider this like these arrows are not there. So if I start at E and I want to reach say F or something. Okay, so you can see there is a path like this and like this. I can reach F. There are multiple paths actually. So this also, so even this third path which is there, right? There are three, there are multiple paths you can take to reach this point, and the fourth point is that
Good evening. Oh,
is
I think the slide is not moving. You're on the same slide.
is it um,
Yeah, it is on that interactive session
is it
slide. Yeah.
okay, okay, so now did it change for you guys? Okay, okay, so it's I'll try
And
presenting once more.
it is not in the presentation mode.
So now it's in presentation mode, right?
No, no.
It's still not in presentation mode, is it?
Left side, I'm seeing all these slides.
Okay, I'll unshare and reshare once. I'll try that. So, let me just do one thing. I'll just share my entire screen.
Oh, it moved just now. You just try that.
Okay, so now it's visible, right? Now PowerPoint is visible.
Yes, yes, it is.
1 second. There are still people. Yeah. So, yes, PowerPoint is visible. Now is it in presentation mode?
Yeah, yes, it is now in presentation mode.
Okay, so I'll just. So now if I write something, can you see all these red marks?
Yes, yes.
Okay, sure, cool. Then I think we can go ahead. So, so yeah. So yeah, I'll just start over. So as I was saying, we'll discuss some of the week 3 content, and then I have some sample problems as well, and then we'll take up doubts for week 3, right? So the first thing that I wanted to discuss is graphs. So graphs have vertices or nodes. So these are the nodes, and these are the edges. Uh, can someone confirm if all these marks and the presentation is working now, right?
Yes, red color marks are visible.
Okay, okay, cool. Okay, let's go ahead. The vertices sometimes called nodes. The edges, and they're connected by edges. So if the edges have arrows on them, they are usually called. It usually means that it's a directed graph, and if they don't have arrows, then it means it's an undirected graph, right? And the edges also usually have some weights associated with them. We'll see what the importance of this is when we discuss ANNs, artificial neural networks. So one important concept is, so for a moment, let's consider that these arrows and all are not there. It's an undirected graph. So a graph will be called connected if I start at any random point in the graph and I can reach any other point in that graph, right? So say I want to start at G and reach B, let's say. Okay, so yeah, you can see there are multiple paths. I can take this path. I can take so till here till D, and then I can go like this and go like this also. So yeah, there are multiple paths. And if you start at any point in this graph, you will easily be able to reach any other point, right? So this graph is connected, and otherwise it's called a disconnected graph. And the next concept is a graph is called acyclic if it does not have any loops. Okay, so in the case of an I'll just So I'll just rub this off. So in the case of this graph, like so in the case of this graph, in it's a directed graph, right? So we are also always have to follow the arrows. If it was not directed, then this S D B would have been a cycle. But in this case, it's not a cycle. Like D does not point to B, B points to D, right? So I So there are no cycles in this particular graph, but yeah, if there are no arrows, obviously you can form any number of loops you want. And even if there are arrows, if the arrows are forming a loop, so say this C, E, D. So if this arrow was flipped, say if arrow was pointing in this direction, so then C, E, D would have been a loop, and we'd call it a cyclic graph. Okay, and so the main thing note here is when you move to the next concept, it will be important. So a connected acyclic graph. Okay, so a graph which is connected, which means I can reach any point from any other point, and it's acyclic. It does not contain any loops. These kinds of graphs are called trees. Okay, so this will be useful when we discuss decision trees. Um, Okay, so there is something called a Hamiltonian graph, which someone had asked me a doubt for the last time. So I'll answer the doubt as well as we'll work through some problems on this. So a Hamiltonian graph is a graph where so it's a connected graph. First of all, it's a connected graph, and there exists a closed loop which passes through every vertex exactly once. Okay, except the vertex where you start, so it will like start and end there. So but every other vertex, it should pass through only once, and while traversing through this loop basically, there we should not be repeating edges. So say like I should not, so I already went from A to B, say then at any other point it should not be like I am going back from B to A. I should not be reusing this edge. So this edge is used only once, right? So in a Hamiltonian graph there are two sub parts, you could call it. One is called a Hamiltonian path. So a Hamiltonian path is just a walk on this graph which connects all the vertices. So it does not have to form a closed loop. So and a Hamiltonian circuit, however, is a walk on this path where we return to the starting point. So this is a very simple Hamiltonian graph which you can see. So now let's look at these two examples on the bottom. So can someone work out and tell me so for this first graph, can you tell me a Hamiltonian path?
A B C E D.
Yeah, ABCD works. ABCDE also works. There are multiple Hamiltonian paths here. So you could, it's not necessary to start from A. You could start from anywhere. You could start from B. So I guess
E
B
D
A D C
A.
E would work. Yeah, B C E D A would work. Anywhere if you start on. So if you, yeah, even if you start at C, there is a path which is there, CBADE, right? And can you form a Hamiltonian circuit now using this? So Hamiltonian circuit is we take a walk and we have to return to the same starting point.
D E A. Yes.
Yeah, so there's one very simple one which is A B C E D and back to A, right? This works even for the B one, so B C E D A and B. Yeah, we will call a and yeah, by the way, so if there exists a Hamiltonian circuit in the graph, then that necessarily implies that there is also a Hamiltonian path, because you could just like delete the last edge and call it a Hamiltonian path, right? So in this case, A B C D E A, right, was a Hamiltonian circuit. So if I just like delete this, not delete actually, but like just not consider this DA. So my circuit is A B C E D A, right? So if I just don't consider this, then this A B C E D is a Hamiltonian path, right? But the presence of a Hamiltonian path does not imply the presence of a Hamiltonian circuit. and the presence of a Hamilton. So if a graph has a Hamiltonian circuit, then it is a Hamiltonian graph, right? But if it just has a Hamiltonian path, we can't say anything. We have to check for Hamiltonian circuits as well. So in this second example, can you tell me a Hamiltonian circuit which which works?
A, B, C, D, A.
No, that does not connect all the vertices, right? So E and F are left out.
Okay.
F A B C E C D A.
Now you can't be going back on EC, right? You can't be going back in this direction. You have already used CE, so you can't be going back. You can use
Start
this
with
edge
E,
only
no?
once. You want to start with
With
A,
E.
B, C, D, A.
ABCDA does not connect all the vertices, right?
Yeah, you
You
start
have
with
to
E,
connect
no?
all the
E.
vertices.
You have to connect all the vertices and use each edge only once to form a
But
Hamiltonian
then
circuit.
then you cannot connect F and E, right?
Yeah, that's right.
Which is not connectable.
Yeah, it's not connectable. So this graph does not have a Hamiltonian
There is
circuit.
no circuit.
That there are no
There is no
circuits.
circuit in
Yeah.
this. Yes.
Can you tell me a Hamiltonian path? No circuit.
Hamiltonian path is F A.
Yeah, no circuit.
Path also. No.
A B C D.
All the vertices have to
And
be
all the
involved.
vertices F A B C F A D C.
No,
No,
it's not possible.
it's
It's
not
not
possible
possible.
also.
It is not possible. There is no Hamiltonian path or
There
Hamiltonian
is no
circuit for
path
this
also.
graph. Okay. So yeah, there are some couple of more examples which I have. So let's work through them. Uh, yeah. Okay. So in this case, we'll look at the left hand side. This one first. Can you tell me a Hamiltonian circuit? So the main question is this a Hamiltonian graph or not? So for that, the best way to check is if you can form a Hamiltonian circuit. If there is at least one circuit, then it's a Hamiltonian graph, right? So can you form a closed loop?
But you said if it has to connect all the dots, right,
Yeah,
for a circuit. So it
yeah.
is not a Hamiltonian circuit.
Yeah, this one, in this case, you can't connect all the vertices via like any path. So so someone might say we go from A, B, C, D, E, E, A, and F. Like you are using unique this thing paths to reach F and connect F also. But then you would be passing through this vertex twice, right? Like
Twice.
Yeah.
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 Yeah. So
So
the
you'll be
second
passing.
circuit is circuit. The second one.
Yeah, we'll come to the second one later. There are some few more things I want to discuss here. So, is there any Hamiltonian path then? If there's no circuit, at least is there a path at least for this graph?
Path is also not possible because
Yeah, a path is also. Now, a question is, can you add one connection to this graph which would make it Hamiltonian graph? And you had one connection somewhere which would make it a Hamiltonian graph.
You're joining E and F, is it?
Yeah, that's
F and
right.
E.
Yeah, so if you just join, so if this connection existed, then I could have easily formed a Hamiltonian circuit here. So A, B, C, D, E, F, and yeah, this would have then been a Hamiltonian graph, but unfortunately E and F are not connected. So for the right example, I wanted to tell me at least three paths. Okay, so at least three paths which work, three Hamiltonian paths, and it so say I put the constraint that it has to involve this. So one of the paths at least has to involve this edge. So this GC edge, right? This one.
Okay, I got one. B C
This one second.
D E
B.
G
C,
F.
one second, one second. Can you repeat that a bit slower? I'll write it down for everyone to see. BC.
Okay, B C D E
Yeah.
uh, G F A and B.
G F A and okay. Right. So B
B,
C D E G F A B. Yeah, that works. Yeah.
but B came
This.
twice, right?
This is a closed
Yeah,
loop, right?
because it is a circuit, no?
It's
Circuit
it's
has to
it's a
end with
circuit.
the
Yeah, it has
point
to
where you
end
started.
with the. It has to end where you start. So,
Okay.
like if I just stopped at A, then it would have been a path, right? So it is not closed. So just to close the circuit, I go A to B, right? So I need two more paths.
Yeah. A F G
A F
E
G
D C B A.
E D C A F A
G.
F G E D C B A, right? Okay, that
Correct.
also works. Uh, so neither of these paths have yet used this GC correction just talking about.
You need with GC connection.
Yeah, at least one path with which uses GC or CG, whatever. The direction does not matter.
Okay. GC. Okay, it can be GC D E F A B. No,
GC.
again it has to come to G. No, no, no.
Yeah. Okay.
Okay. Sorry, sorry.
Yeah. No. No. No
G
problem. No
C.
problem.
No,
Yeah. Yeah, keep trying.
no, no,
No issues.
no.
G C D B. Then A F
Second.
E G.
GC. Can you repeat that? GC
G C D B
DB
A
A
F
F
E G.
G. Okay. Yeah, that works. GC GCDB AFEG, right? Yeah, that works. So yeah. I have I think I have one more example. This one. Sorry. Yeah. So in this again, is there a Hamiltonian circuit which you can find? Is this a Hamiltonian graph? Is the main question.
Yeah, I think many will get at least four. E B A D C E.
So
A D C E.
EBADCE. Yeah. So this just this existence of this one part means it's a graph, it's a Hamiltonian graph, and I think if you start at E, go in any direction, you'll be able to end up at
Yes.
E again. So what about if you start in the corner? So I haven't tried it. Yeah, even if you start in a corner, you'll be able to reach. So BAEDCB, right? So BAEDCB. This is you start at a corner. Any corner you start at, you'll be able to reach it.
Okay.
So yeah, this is a simple example. We'll move on to decision trees. So I don't have a lot of material to discuss on decision tree. I would rather solve an example where I show you how to make a decision tree from scratch. So I'll explain this table first. So the table is that so there is a chemical plant, and there is someone wants to use a chemical in this plant, and the system has to see whether to accept this request or reject this request, right? So there are four levels of you could say checks. There are 4 checks. So the first check is if the requester is authorized. So if this is false, then just ignore this requirement number. It is not like it just means all these levels are fulfilled. So the first check is that if the requester is authorized. So if it's not authorized, then the request is rejected. If the requester is authorized, then the second check is that if the chemical is available. So if it's not available, then you reject the request. So if requester is authorized, chemical is available. Is the chemical hazardous? If it's not hazardous, you can accept it. Then if it's hazardous and the requester is not trained, then you reject the request. And finally, if everything is successful, then you accept the request, right? So yeah, I would want you to tell me a structure of a tree which you can make out of this.
Decision tree.
First one is a
Sorry,
request to.
I didn't understand your question.
Okay, so we want to make a decision tree from this table. So how can I convert this tree into a table? This table into a tree, into a decision tree. So there are 4 levels, right? And at every level, we are making a particular decision to either accept or. So the final action is accept the request or reject the request. So how would we convert this table which I have here into a tree?
So the topmost one is request is authorized,
Okay,
and
so
bottommost is accept or reject.
I'll call this 1, 2, 3,
Three,
4.
four.
Yeah, because I don't want to write on this. So if first I have 1, right? So if I have requester is authorized, so there are 2 possibilities here. So one
True or
is
false.
yes, yeah, okay, okay. Let's go with true and false. True and false. So if it is false, then the answer is no, right? If it is true, then I will check 2 basically, right?
Yeah.
So again, there's true and
If it
false.
is true or false.
Yeah.
If it
So
is
if it
true,
is first, let's see if it is false because it comes. You can easily check that. If it's false, then it's basically no. And if it's again true, then we'll move on to chemical is hazardous or not, right?
mm,
So if this is true, and if this is false, so if this is false, then the answer is yes, right? Sorry, the computer is lagging. Anyway, so and if the chemical is hazardous, then you move on to 4 or fourth check, which is if the requester is trained or not. If he is trained, then finally answer is yes, and if he is not trained, then the answer is no. Right. So this completes. So you can see that there were 2 accept requests. So this and this, and we have 2 yeses here. So makes sense. There are 3 reject requests. So there are 3 no's which you have, right? So this is a very simple example. There are so if there are more columns, then obviously this tree gets bigger. And yeah, does anyone have any doubts in decision trees, like this example, or in
yeah,
general, if you
it's
want to
fine.
ask me? Okay, cool. So yeah, we'll move on to Bayesian belief networks then. So Bayesian belief network, it works on the principle of Bayes theorem. So I'm sure you know Bayes theorem. So if I have 2 events A and B, and A causes B, basically. So I know the independent probabilities. So usually what happens is I know the independent probabilities. I know the probability with which A occurs, and I know the probability with which B occurs, and I know the probability of B given A. So basically probability of effect given cause, right? So usually what we want to find is the probability of cause given effect. So say this would be something like so an example would be like so say someone is sick, right? And so you want to like they have some symptom, and you have some diagnosis, right? So usually you would know the probability of the symptom occurring if you have the diagnosis. So the diagnosis is the cause I'm talking about, and the symptom is the effect of this illness. Usually you would know what. So this is my diagnosis, and this is my symptom. So usually I would know this probability, the probability with which the symptom occurs given this illness. What I usually want to find out is, so the bigger question is, so what is the disease or the diagnosis or the illness given that I have some particular symptom, right? So this is not a very like uh, a very nice example, because these probabilities are probably harder to like rationalize. But anyway, I mean, you get the idea that I want to find the probability of some illness which I have given some symptom. So I would do it in this way. So these three probabilities are usually known, and this is unknown. So you find that. And so Bayesian belief networks, or just they're sometimes just called Bayesian networks, they are basically graphical models that represent a set of variables and their dependencies via directed acyclic graphs. So these two words are very important: directed and acyclic. So it has to be directed. I mean, it has to have arrows on it, and it has to be acyclic. So it should not have any cycles anywhere inside the graph, right? So I mean, I'm sorry, I think this a little bit of the text got covered here. Let's quickly hide that. So yeah, okay, yep. Okay, so the most important use of these networks is to, so we will start off usually we'll start off with some probabilities we have in our models, like through some modeling we have found out some probabilities, but then we would actually want to update them based on our observations, right? So these networks are used to revise the probabilities based on our actual data, our actual observations, right? So this is a directed acyclic graph, you can see. So it has arrows, it goes forward, and it does not have any cycles in between. So I'll go to the next slide. So again, there are two images I have. So are both of these Bayesian belief networks? That is my question. So the first one is anyway the same as the previous slide. So it is Bayesian
The
belief
second one
network.
is not, because it is forming a closed loop, no? This arrow, this arrow, this arrow.
Yeah,
So it
that's
should
right.
not form a
So
closed loop.
so there is a closed loop here. So here this. So this is a closed loop which it is forming, and this should not be the case in a Bayesian network, right? So the physical interpretation of this is this violates kind of the cause and effect principle, right? So this point, so there would be a vertex here, right? And then a vertex here. So this causes this and this causes this, but ideally, so this C basically should be a, call it ABC. So this C should be an effect of A, right? But in this case, C is also causing A, which does not make physical sense, right? So this is why we can't have cycles in a Bayesian network. Okay, I'll move on to our next concept. So yeah, I mean, if anyone has any doubts, you are free to stop me anytime and ask, right? So it's not like I keep talking. Anyway, so an ANN, it's a connected and directed graph, right? Connected means I can get from any point to any point, right? And it's directed. So I have written connected here, but it's also directed, right? So usually you won't be able to. So say if I start here and I want to end up here in the like backwards, so usually this directed thing will prevent that. But if you just slightly disregard that direction, then it's a connected graph, right? So here is where we'll see what the meaning of these edges having a weight means. So these edges will have a weight which can be adjusted. So this adjustment helps us increase or so if the weight increases, so say this one connection weight increases, right? So that means this connection becomes stronger, and say this one decreases, so this connection becomes weaker, right? So this is how we physically interpret it. And each node, so here I have a node, right? And this node has let's see, so this node has, so this 1 2 3 4 however many 1 2 3 4 5 6 inputs, right? So this has 6 inputs and how many 1 2 3 4 outputs, right? So this entire thing, this entire uh, like entity with the node along with its inputs and outputs is called a neuron. Okay, so this is where we derive it from how our brain works and how neurons look actually in our brain. So these neurons are usually, they are grouped into these layers. So this is so usually there will always be an input and an output layer, and there may be so in input and output layer is always there, and ideally there should be at least one hidden layer if not more. So the more hidden layers you have, the more complex this network gets. So you can have hidden layers with as many number of neurons as you want, right? So like if you have say 10 hidden layers in between, and then you have your output layer, that is that also works usually. Like such deep networks, so like this the if when the number of hidden layers increases, we say that the network is becoming deeper, right? So this is where the term deep learning comes from. So deep learning is basically neural networks which have a lot of layers, a lot of hidden layers, right? So typical deep learning models would have, say, so the ones which are commercially used, they would have around, there's 16 hidden layers, 19 hidden layers. Some even have 32. So yeah, usually people love to keep it in uh, like in powers of 2. So 16, 32, right, 64, right? So this is some like this is like makes our computations marginally faster. So this is better sometimes. And yeah, so the that's what a deep neural network is. A deep neural network is nothing but a neural network with a lot of hidden layers in between. Okay, so what is this neuron now? So I've shown a simple model of a neuron. So what happens is usually there's also something called a bias b, which is input here, right? So the bias is basically each neuron will fire if there's a if it crosses a certain threshold, right? And we call the minus of the threshold. So minus threshold is equal to b, right? So b is the negative of the threshold which we put into this, so that so that we can say that if the output of this cell is greater than 0, then this thing will fire, right? Which means if my inputs are crossing the threshold, then this cell will fire. So what happens is we have these weights, right? So we have so this edge will have a weight W0. This is W1, W2, and we have our inputs also X1, X0, X1, X2. Then we'll multiply the weights with the input. So W0 X0, W1 X1, W2 X2. Add them, add our bias, and then we have our cell. We know if it is ready for if it is ready to fire or not. And then so before the output is sent out, we usually use something called an activation function to like introduce some non-linearity basically. So what will happen is, if you don't, you can also choose to not use an activation function, but in that case this network, so this entire complex network would be nothing but linear regression. Like you could, so this entire model would just boil down to like of finding a linear relation between inputs and outputs, right? So and I just shown here one graph. So say this output, this input, and if you have no activation functions, then this would just be like trying to find a linear relation between them. But since we are using this activation function, this introduces this non-linearity into this network, and hence it can like so we can obviously model very complex relations between output and input, right? So anything, right? uh, I, I don't know what the final output would look like. Anyway, it's a multi-dimensional thing, so we would not be able to even visualize it. That is how a neuron works, and that is how a neural network works. So this network just works on this principle. We have some inputs which we are giving to the input layer, and then each input is connected to every neuron in the next layer. So these neurons are obviously connected to every neuron in the previous layer. They get their inputs from here. We have our weights, and finally we call this. So so as we move through the network, we are calculating the inputs and outputs, and finally we get our four outputs. So this is called feed forward network, right? Feed forward. Yeah. Okay. So this is called a feed forward network, and what we learn from an ANN. So why we use the data and what we want to learn in are these weights. Basically, I want to use my data and use the structures network to update my weights, right? So I want these weights to be updated, these connections. So all these connections, so some of them will become stronger, some of them will become weaker, and in the end I will have a network where if I put these inputs, so it just goes through this feed forward calculation, and it can give me a correct set of results which I am expecting, right? So in order to train this network, I will require a lot of data, and I will also require that like the targets basically. So this is again something of, so this is a supervised uh, so this is supervised sorry anyway. So this is supervised network, right? So this is supervised algorithm. I have some targets which I want to fulfill, and I have some input features, and I put those input features, pass them through this network. I check what outputs I get using some existing weights, and then there is something called, so you'll learn in the later weeks, there is something called a back propagation algorithm, so a backward algorithm, which basically which basically allows me to use my output and the ideal output, and I take the error and I can use this error and feed it back to the network, right? And using those errors we can update those weights. So we can assign, so basically we can think of like so this neuron with this connection, so this has caused the error to go up, right? So we will choose to reduce the weight of this connection, or say this connection is making the error go down, so we'll increase the strength of this connection, right? So this is how we try to figure out. And this combination of this feed forward and back propagation algorithm, so this is how you train a neural network. And after training, then it's only the feed forward direction, we don't need back propagation anymore because we're not training anymore. So we just give some unknown input features and pass it through this network, and it will give you the output features, or the output thing. So usually this would be, so if it's a classification task, so say this is again cars, trucks, buses, bikes, say. So, and these are some image features which you have obtained. So it doesn't have to be like 6 features. It can be any number of features. You can also directly pass the image. Okay, so if you directly pass the image, we use a slightly different structure of a network, which is called a convolutional neural network. I'll just write it down. I won't go into details about this now. Convolutional neural network, right? So this is named because there is an operation called convolution which we do in this network, in that sort of network, and it has been found that it is really good for working with images, right? So it is very powerful when working with images. You can obviously use a so this is sometimes called CNN. So you can use a CNN for anything, but it is most powerful when it is used with images. Right. So say I have some input features and my output is like cars, trucks, buses, and bikes. So usually this would be the so the input image, say, which I passed. So the output would be the probability that this image is a car, truck, bus, or bike, right? And I would choose the one with the highest probability. So say the highest probability for a particular to be bus, right? So bus gets say a zero point 0.7 probability, truck is like 0.5 or something, and it is not necessary that these four probabilities have to add up to 1, so it can be anything, but the one with the highest probability, so this zero point 0.7 thing I will choose, and say that this image which I had passed was a bus, right? So, and hopefully it is correct, like after training the network, hopefully this answer should be correct. So, do you have any doubts on this concept of an artificial neural network?
Okay.
Okay, cool. We'll go ahead. Yeah, I don't have much to. So this is my last slide. We'll start with the doubts after this. So I'll just discuss genetic algorithms. So these are a class of. So these are a part of evolutionary optimization techniques. So this uses the concepts of natural selection and evolutionary biology basically to form different kinds of algorithms. So there are a lot of evolutionary algorithms. Uh, there is something which is related to ants. I am forgetting the name of this of that. So there's an optimization techniques which is related to something along the lines of how ants build their nests or something like that. So it's also very interesting. I'll let you know next time. So so this technique is used to generate so global optimal solutions for either optimization or search problems. Okay. So usually the easiest way to work through a genetic algorithm is we have our set of data items, and we'll convert them into binary strings, right? So every data item which is there, so say there are like, so say I have, so this set is called a population, by the way. So my initial set is called my initial population, and I'll have a number of data items there, and I will convert them all to binary strings. So and After I convert them, I can calculate something called their fitness by using a fitness function. So there'll be a fitness function which is either defined on these binary strings, or it is defined based on I can convert this binary back to like base 10, right? So what would this be? 8, 10. This one is 32, right? 32, 8, 40, 42, and 43, I think. So yeah, if I'm wrong, I mean it doesn't matter. There might be a fitness function which is defined on this number, or it might be defined directly on the binary string. Like you can use binary mathematics. And so after calculating the fitness by using this number, whatever, or however the fitness is there, we'll have some fitness values. We'll choose a percentage of the highest fitness values, and then what we'll do is, so this group of high fitness values which I choose, right? So this group, the smaller group, this will form the parents for the next generation, right? So I will take pairs of data items from here. I'll take two items from here, and I will mate them. I'll make them reproduce, right? So how you make them reproduce is something called through two process, crossover and mutation, right? So crossover means basically, I'll explain here. So this is the case of multi-point crossover. So again, someone had asked me a doubt about two-point crossover last time. So two-point crossover is a special case of multi-point crossover. I'll explain that first. So what happens is basically, say I want to do a three-point crossover. So I will choose three random places where in these strings. So these are my two parents, right? So this is a parent and this is a parent. And so I'll choose three random places where I want to cut these strings. And what I'll do is, so alternatively, I will switch the bits. So this rectangle basically represents 1 1 0 1 1 1 0, maybe like 1 0 1 1, whatever, like 0 0 0 1 0 0. Okay, something like a set of like ones and zeros, and I'll choose these cutoff points, and so the first parts remain the same, right? So this goes to this. The first part. So these are the two children, right? The first parts remain the same. The second part is flipped. Third part remains the same, and the fourth part is also flipped, right? So in two-point crossover, so if you just ignore this for now and say our string is just this long, so so this would be two points that I choose to cut, right? So the first and last bits remain. So again here I am not considering these. Um, okay. Yeah. Anyway, so so in the children again, so the first and
That is
last
the
part remains the same.
three point crossover you are explaining, right?
Yeah. So what I explained was three-point crossover. Someone had asked me a doubt about two-point
Yeah,
crossover. So it is
I only
just
asked, but yeah,
yeah. I mean, so it's just I mean, a special case of like. So say I only have these many bits. I'm just considering that like this is the length of my string now up till here, and I have two cutoff points, right? So what I'll do is this first and last part remains the same. I'll just flip the bits in between, and that creates my two children, and I have a two-point crossover like this, right? So does that clear your doubt?
what I was with the 8-bit string, and it is the crossover points are first and the last. So in between, everything has to be flipped, right? That's
Yeah,
exactly what.
yeah, everything is flipped.
Yeah,
So it
yeah.
can't be like if I have 8 bits, it can't be like my points have to be in between anyway. So these two, like
So
choosing
if
the
the
cutoff
question
points will
mentions that,
be between.
yeah, if the question mentions that instead of randomly selecting the cutoff region, they specifically saying that it is between the
Ha,
first
yeah.
and the
I
last.
mean, yeah. If it's a question, then ideally it should be specified. But when you actually do GA, like when you apply this algorithm, usually this like the cutoff points are also chosen randomly between the first and last bit. So we'll have some particular length. So of the strings remains constant throughout the algorithm. It's not like the strings will increase or decrease in length. So we can say that. So say if I want to choose two cutoff points, say I'll choose two random numbers between like 1 and 8. So if I choose two random numbers between 1 and 8, then I have my two cutoff points, and I can do crossover, right? And mutation is simpler than this. So in mutation, what happens is, so I have now, so crossover is always done first before mutation. So mutation is always applied on the children. So what happens is, after crossover, I have, so say so initially say I had 10 strings, right? So my next population will also have 10 strings, and say out of these 10 strings I want say 20% of them to have mutations, right? So that means 2. So I'll choose any random 2 children from a set of 10 children, and I'll just flip one bit in between. So I'll make some random 1 into a 0. I'll make some random 0 into a 1. Okay, so where you want to do this is up to you. I mean, in the program you can do it however you want. You can choose a random location and do there. So you can let the computer choose the random location. And the thing is, you just flip one bit into the other, right? And if you want to do multiple bits in the same this thing in the same string, so you want to flip 2 bits in the same string, then usually that will be mentioned. So and I mean, you can if you are applying it to real world problem, then you can do whatever you want and just choose to flip 1 bit, 2 bits, all bits. Okay, so but usually if it's solving a question, then it should be mentioned that we are trying to flip 2 bits, right?
Yeah,
So
it looks like crossover and mutation looks like same, other than number of bits are
no,
different.
crossover and mutation is not the same.
Crossover comes before mutation.
Crossover comes before crossover is always done first. So I have 2 parents. So and crossover will be like I am shifting this group. I am exchanging the bits. I am not flipping any 0 into a 1 here. I am not taking this 0 and turning it into a 1. That is not what
Okay,
happens.
okay.
I am
So
flipping
bits
these
of the
bits here.
parent is taken.
Yeah. So I
Bits of
choose
the parent.
these slices, and I will flip the slice in between for 2 point.
Okay, okay,
I'll flip the slices alternatively, basically. So
okay,
here and then skip one section, then the next section, like that. But in mutation, mutation involves only one string. So I have one child, and I'll so say this child has something like 1 1 1 0 0 0 1 1, right? So it has something like this at the end, and I choose to do mutation, so I'll take this 0 and turn it into a 1, right? So this becomes 1 1 1 1 0 0 0.
okay,
So this is a slight change, but yeah, I mean, it encourages it encourages like new features to develop, basically. So this is how natural selection also works, and you try to replicate it here through this simple flip of a bit. Right.
okay.
So this is all that I had to discuss. If you guys have, I'll keep them. So
What is that 43? What? I mean, like I
sorry,
was not in a little arithmetic.
sorry, 43.
That is
Oh,
2 to the power of
43.
0.
Uh,
Numbers, binary numbers represented
oh,
in
this,
decimal.
so say I have some string which is like this, which is represented as 101011. Then like, and I want to calculate the fitness. So the fitness function may be defined on this string, or it may be defined on this number which represents the string, the base 10 number which represents. So I just converted this. number into.
Now, what's the fitness function? It is the second step, no? After generalization, you go for the fitness function, right?
I mean, the fitness function can be chosen based on. So, say if you are trying to do a maximization problem. So, say I have something. So, I can't seem to write here. But so say I have something of like a function basically, and I want to find its maxima. Then I can use a GA to, and the fitness function would be the function, right? And the fitness would be the value of the function. Like say I have x square plus 5. I want to find the maxima, the maximum minima whatever of this function. So x square plus 5 will have minima. So say yeah, minus x square plus 5, right? So this will have a maxima, and I want to find out where that is. So and what the maximum value is. So I can make my fitness function minus x square plus 5, and then I can work from there, right? So it can be anything, depends on the problem, very problem specific, and the choice of this fitness function is everything actually. So if you choose a better fitness function, then your GA will start performing like uh, like at a much better level than you expected. But if the choice of fitness is not great, then the GA will not like it will not converge basically to a particular solution. So yeah, I mean now I don't have anything more to discuss. If you guys have any doubts, some people want to chat. Anyway, so if you guys have any doubts, you can type them in the chat. You can talk about it.
This bucket bridge phase, what
Yeah.
does it refer to in the classifier system?
So in classify, I will go back to our professor's slides. So can you just quickly point me to which lecture this was in? I'm not able to see it. If you point me to the lecture, I can quickly give you an answer. Anyway, so you're talking about bucket bridge classifiers, right? So,
1 second, I'm just going through that.
yeah, sure. And also, quickly, quickly,
Maybe it's in the logic programming.
logic programming, right? Yeah.
Mm.
Okay, so I mean, I have to admit, I personally don't have a lot of experience with logic programming, so I might not be able to answer every question on this. So, yeah, and see, maybe, yeah, even actually, I don't know it, so maybe so, that's why I'm unable to answer it. So, I'll try to answer you next time again once I find the answer to this. So, yeah.
Yeah, it's called as in the classifier system based on genetic algorithms. The bucket bridge
Okay.
phase refers to specific stage in the evolution of the system. So it is in the genetic algorithms only. It is a specific phase in that. It is as compared to something like the fire people attending. It's like dividing everything data into clusters and then when connecting them, and this becomes the most essential crucial. Like it's
Oh,
a
okay, okay.
classifier
Classifier
system is a genetic involves a set of
applications.
rules called classifiers. The structure allows for efficient and accurate classification of input data. In bucket bridge phase, the genetic algorithm repeatedly selects, recombines, and mutates classifiers to produce new generation of classifiers. Over
Oh,
time, the
okay, okay.
classifiers in the population evolve to form a set of bucket rules that divide the input bridge space into smaller regions and a set of bridge rules that connect these regions. The bucket rules helps simplify the classification process by dividing the input space into smaller, more manageable regions, which the
Okay.
bridge rules provide the necessary connection to accurately classify inputs based on their specific characteristics.
Okay, so what it seems like to me is based on what you read out.
I mean, the overall
Uh,
goal is to evolve a set of classifiers that
yeah,
efficiently
yeah,
and accurately categorize inputs based
yeah.
on their
That's right.
characteristics.
That's right. That's right. That's right. So it would, yeah, yeah. That's right. So it would find the most optimal or the most
Essentially,
optimal
this,
set of
yeah, yeah,
classifiers
this
for a
is
problem. Yeah.
a bucket bridge algorithm. So
Okay.
credit
Yeah.
and blame to the
So,
individual contributing classifiers.
um,
So uh, credit and blame is actually given to the individual classifiers something. So there is a credits and blame system there in that. So they take
okay.
the better options and
Yeah. Okay. Um, okay. So yeah, I think you answered your own question. Any next time
no, no.
I'll try to give
I
a
just wanted to have some more idea. Yeah.
yeah, sure. I will.
Let me
I'll
take
try
two
to
steps
give
in the
a.
sequence of rule application. Yeah, yeah. Thank you.
I'll try to give a more detailed, overview to you next time. So yeah. Are there any other doubts?
We discussed about
Yeah.
the different types, no? The 11 types of classifiers that uh, that wanted to discuss.
11 types of classifiers in what exactly?
Like learning a single concept offline from pre-classified positive example. Then it is near misses, outliners, negative examples, online learning, instance-based
Yeah,
learning,
yeah. Okay, okay. I think I skipped.
doing away data items,
I
that
think
is
I,
again
I think I skipped that. That was some
unsupervised
of
learning.
week two's concepts. Yeah, yeah. I'm sorry about that. I have
Week two, sorry.
missed. Yeah, I missed out on that. If you want to discuss it, I will make it a point. I'll write it down for myself. I'll make it a point to discuss it at the beginning of next week's lecture. So
Yeah.
uh, okay.
Week four, would you like to answer something? Week four also
Uh,
has come up now.
Okay, I haven't gone through week four actually. So it just came out when I was preparing for week three. So if
Yeah,
there
but
is, you can
I
try
just want to
asking me.
suggest
If I have some answers, then sure I will.
the proximity solution. I have doubt in that proximity solutions. So maybe next time you could.
Yeah, sure. I mean, next time we'll anyway be discussing week four content. So I'm sure a lot of your doubts will be cleared up. But okay, I will. Yes, I haven't gone through the
The
videos
rest all I
actually.
was somehow
So
able to understand a little bit, but
um, yeah, can you tell me the lecture number? I'll try to search for it and we can. I'll try to answer you if I have answer
the
to it.
the fourth week portion. The lecture number would be the last.
Last, right? Analysis. Let's see.
Yeah, I'll tell you. Yeah, it is cluster analysis.
Okay.
Cluster analysis. Yeah, in that the proximity thing,
Okay.
proximity problem. That's how to combine the things.
So this is discussion cluster problems, right? Hierarchical
Partitioning, I understood.
clustering,
Hierarchical dendrograms, yes. This is
density.
the previous one. No, no,
This is density based clustering.
no. Before that,
Before
different
that, it
types. They
was
are grid based.
dendrogram, right? Before that is hierarchical clustering.
Yeah, I think after this, like I'll just move next.
Okay.
Yeah, this when the table
Dense.
is coming, right? No, no, no. This
This one, right? This
yeah,
one.
this yes,
Okay, okay.
yes. Stop there. This one, this proximity matrix.
Okay. So, okay, this is a
So
different clustering algorithm.
yeah,
Agglomerative cluster. Okay. So this
hierarchical
is
based,
one.
hierarchical based clustering.
Yeah, yeah.
It's a
Hierarchical
distance
clustering.
thing, and
So Okay.
So you're basically
Um,
combining to get a simpler final thing. How we are merging the closest clusters
Acha, okay, okay.
in the
Okay.
step-by-step manner, merges and splits
Yeah,
in a greedy manner.
I have to admit I don't have any experience using this. So I'll try to clear it up, yeah, next time once I learn about it myself. So there are a lot of things which I am also learning from this course, and I'm just trying to explain what I understand
Yeah.
to you guys. So yeah, I'll definitely yeah, pay more attention to this part next time. Yeah. Okay. Thanks for
Then
this chat. Yeah.
before that, in the first
Yeah.
lectures, there is a generalizations. It's slightly in that there
So
is they're categorized as generalization strategies. One is data driven. The first,
um,
just one minute.
yeah. Uh, uh, so this is something. um,
Yeah.
yeah, you're talking about this, right? Generalization.
Generation of data driven strategies. In that we have depth first search, breadth first search, version space, and generate and test is another thing which is general to specific, specific to general.
Yeah,
So when we are using the DFS, yeah, in
yeah.
that the entropy calculations,
Ah, the entropy calculations.
so it is like this distinguishing between inductive learning and analytical learning. In
Yeah.
inductive learning there is plentiful data and there is no prior knowledge. Analytical learning has total prior knowledge but scarce data.
Okay. Yeah. Yeah.
So the
That seems right. Yeah.
goal is hypothesis fits the data
Yeah.
in the inductive learning.
Yeah. That's right.
Then justification is statistical inference.
Ah.
Advantage are require little prior knowledge. Pitfalls are scarce data, incorrect bias, which are
Yeah.
not there in
Yeah.
the yeah.
Which should not be there in analytical learning. Yeah.
But it also suffers from imperfect domain theory, and but it has to learn from scarce data. It has got deductive inference and hypothesis fits domain theory.
Yeah.
Uh,
That's right.
so the entropy concept here and how it actually moves in the trees, the depth first search, basically depending on the negative and the hypothesis, also the positive. So the things
Okay.
are stored. The breadth first, which is specific to
Yeah.
general, stores only the negative and the hypothesis. Then the version space strategies, which is I think storing all the things. So how they are behaving differently. The different strategies
Okay.
uh, in the generalization as a search.
Okay. So you want some more explanation on that, is it? Okay. And
Because it looks very deep.
uh,
I mean, like
okay.
because it
Sure.
has got the processing time storage space. This lecture is a very tightly based structure on a very old lecture which I am not able to retrieve it because it is 1977's lecture on joint
Okay.
fields.
Okay. Okay.
So I don't think they have digitized those days lectures and all. So
Okay. Yeah. Yeah. Probably.
yeah, yeah. So the data driven searches, each one is actually like a BFS algorithm has got all the negatives plus all
Yeah.
hypotheses. And then when
Huh.
the instances are given, how are we choosing the best things using BFS? How
Hmm.
we are doing using the BFS? How we are using the version space approach? Right? It gives like uh, how we are shooting the best hypothesis using the different strategies, the questions based on that. So
Okay.
that part also I'm able to understand. Yeah.
Sure. I'll try to explain that to you next time. So yeah, sure. I'll look into that. Like I'll do some research on that and
Yeah.
come up with an
There's a
answer.
and
Yeah.
then the information gain. Entropy before splitting and entropy after splitting. Minus entropy after splitting.
Yeah. That's right.
And entropy for a decision tree dataset with positive and negative examples. Of course, this all I am able to do it myself. But the thing is the kernel trick, the support vector machine,
Yeah. Yeah.
uh, those things.
So
Partitioning based clustering, hierarchical. Yeah.
yeah, I mean, yeah, I'll discuss if it's in week four. I'll definitely going to discuss it. So
Mm.
yeah, I'll discuss distant tree learning, and yeah, I think SVMs and all will form part of this only. So I have yet to go through the week four content myself because yeah, I mean it was just released some time back, so I have not
Yeah,
gone through
yesterday
it.
they released it. Day before
Yeah,
yesterday.
sure.
Yeah.
Okay, so I'll definitely discuss it in more detail. Yeah. So anyone else has any other questions? Yes. Okay, so if you guys don't have any questions, I think we can end the session. So yeah, I mean, if you have any questions later, the discussion forum is there. I keep checking it. So my fellow T is also check it. So they are answering some of the questions. If you have something, then you can post it there. We'll try to answer it for you. Right. So uh, if you have anything to ask, you can ask me. Otherwise, we'll end the meeting. Okay. Okay.
I
So
just want again
yeah.
need to
Sorry.
repeat
I
that
just
point crossover.
Okay, okay, yeah, sure, sure. I'll do that. Stop sharing. So okay, let's go back to this. Okay, so I'll take a slightly slower approach. So the see the idea is that so okay, so let's just consider 2 point crossover, right? So forget this red part which I have striked off from both things. So just imagine that there is nothing there, right? The string just ends. Okay, my computer is lagging a little bit, but anyway. So I have this string, right? So again, say 0 1 1 1 0 0 1 0 0 1 1. Right. So I have this entire string, and I have another string in at the bottom. So what I'll do in 2 point crossover is, so I will so in my GA code, I will randomly choose 2 points where I want to cut this string, right? So I have, so now these two anchors are in place, and what I'll do is, so for every, so the first part of the string remains the same, and after that, so every alternating place will flip it. So in this case, only in the middle will flip the bits. So all the bits in this gray string will come into the blue string, right? So this is what happens in the children. So the first parts remain the same. The first part is blue here, the first part is blue here, second the first part is gray in the second string, first part is gray in the second string. But in the second part, so the second part becomes gray here, second part becomes blue here, right? So basically, so all this 101100 whatever I've written, exactly the same thing will come down here, right? So 101100 100, right? So exactly the same thing comes down here. There is no change. Just this blue, just this part of the string is flipped with the gray, the whatever ones and zeros are there in the gray part. Right. So this is what 2 point crossover is. And again, the third part remains the same. Like this part remains blue, this part remains blue. Right. So this is the primary method of reproduction in GA, and after this you will apply mutation. Okay,
Yeah.
I
So
hope
the
that
last question
clears
is
it.
about this
Yeah,
fitness
sorry.
function, and then
Yeah.
fitness function. How do you select it?
So it is entirely dependent on the problem at hand.
Hmm.
So there is no general fitness function which should work for all genetic algorithms. It is completely dependent on the problem. So usually the simplest example of using a GA would be to find the minima or maxima of a function. So say like, yeah, as I mentioned, say f of x is minus x square plus 5. So in that case you could just choose the fitness function to be minus x square plus 5, and you would have, so my inputs, my data items, basically my population would be consisting of these random values of x, right? So any random value of x, I'll take different values, I'll convert them into binary strings, and I'll also be evaluating the fitness. So the fitness is based on the base 10 number, but the strings are used for so every string is used for this mutation and crossover. And after we have generated, so the point of the reproduction is that we'll generate new numbers which the function can try until we find the maximum value. So usually the strings will converge into one. So at the end, all ideally all the strings would have the same value. So all the strings would be the same in the final population. So that is where we say that the optimal solution is reached. Or otherwise, like usually there is some sort of termination criteria we set. So say like just generate 10 populations and not more than that, or 10 is very small. Usually you will go for 1000, 10,000, and we'll say that after say 1000 populations have been generated, then you can stop the GA, and whatever is the highest fitness value at that point, we'll consider that as the optimal solution. So usually that works for most cases, but yeah.
The Bayesian networks. What exactly is the principle of Bayesian networks?
So they work on the principle of Bayes theorem. So I explain Bayes theorem, and so Bayesian networks, they are also actually used to find yeah, sometimes used to find optimal solutions for some problems. So and but usually they are used to, like update probabilities of events based on the data which you have. So it is highly efficient in that way. But yeah, I mean it can also be used for optimization problems. I have seen it used for optimization as well. Yeah,
So there are some prior probabilities, right?
yeah, there are some
Based
prior
on which
probabilities.
you calculate.
So we can I mean those are based on I mean previous knowledge.
And there is a
And
probability
yeah,
that there is a
yeah,
and there is
yeah,
a probability that there is a effect because of a cause.
yeah, that's right.
So we can cause what causes what effect will have, what is the cause of that effect, right? From that,
Yeah, yeah, that's right.
if you have this
Ha,
information,
ha, yeah, yeah.
like for example, yeah, person is suffering. So what is the cause of which came first, or
Ha,
which
yeah,
is the
yeah,
effect?
yeah. Yeah. So if there are multiple causes, then you could also find the, the probability with which, like, which cause is more likely to have caused this event, something like that. So you could also find those probabilities. So and the data is is then used to update these all of the existing probabilities, and you can again go back to calculating which cause has more probability of causing this effect, and yeah, things like that. So yeah, that is where Bayesian networks are most used.
Yeah. So what
Okay.
is bias
Bias.
introduced in that, and what are the weights
Okay.
actually?
So bias is
The
basically,
artificial.
yeah. So usually, so in a neuron, I would not want to fire. So usually, I would not want to fire the neuron unless it crosses a certain threshold value, which is, I mean, it can be very small, it can be very large. So the bias is also something which is trained by the, so which is also updated as the network gets updated. So so what happens is I would not want to fire this neuron, right? So I have this neuron here. I would not want to fire it until it crosses some threshold value. Okay. So what I'll do is I'll add minus the threshold here. So plus b. So b is minus threshold, right? So if I do that, then instead of having, instead of having sigma wixi greater than threshold, instead of that, I can have sigma wixi plus b greater than 0. Okay, so this is much simpler. Like I don't have to keep changing these threshold values for every neuron, right? Every neuron might have a different threshold which I want to activate it in. So I don't want this inequality which is there to be changing all the time, like on the right hand side. I just want it to be a constant. So I just add the bias on the left side and call it. So if this neuron, so the output of this neuron now is sigma wxi plus b, right? So yeah, sorry. So
Hmm.
now I'll fire this when this quantity is greater than 0. I'll fire this neuron. So that is my condition, and like keeping all the variables on one side of your inequality or equation. That is the goal basically. I mean, you can choose to have b on the right hand side, like sigma wxi greater than minus b. That is also a possibility, but usually we just add the bias and say that if this cell reaches value greater than 0, we'll fire this cell. So that is easier to implement basically. And weights are, again, so weights are basically the strength of these edges, right?
Connection factors.
Yeah, connection factors, yeah, you can call them. So if a weight increases, then this connection strength increases, we say. If the weight decreases, then this connection strength decreases. Okay. So these weights are, again, so through the training of this network, this is what we train actually. So we'll train all these. So you see all these dense connections here, right? So every one of these edges has a number associated with it. So what we train is actually, we will update all these numbers based on the data, and based on what kind of predictions I'm getting, and we'll finally settle on uh, some values of weights which cause this network to create, to generate good predictions. So good prediction means which is very close to for the training set. So the predictions given by the network should match the actual predictions pretty well. So yeah, and once it does, so we will call that network trained. Then after that, we'll just give some unknown input, and it will pass through all of these. So all these, so the input is basically a number or a list or something like that, and it will pass through all of these neurons, and finally it will give me a prediction. Right, and so since I know that this network is well trained, I will believe that prediction, and I will say that. Okay, so if I was giving images, so say this image is a bus. So it says that the network will say that this bus has probability 0.7. Everything else is lower than that. So I'll say that, okay, so the image which was given to this network was a bus,
Hmm.
right? So this is how you uh, like, implement it, and
The
yeah.
convolution neural network.
Convolution neural network. So this will come in much greater detail in later weeks. So basically, there is a particular operation called a convolution, which I won't go into detail now. There is a particular mathematical operation called a convolution, and in the calculation of this, here we are just doing w naught x naught plus w naught x one plus w two x two, right? So instead of that, we'll perform this convolution operation somehow, and we'll then have a particular output for that after we do the convolution operation, and we give an activation function. So it is just a mathematical difference. It is not, and it has been found that the this kind of operation when it is used with images, right? So this kind of network performs very well because it is very fast, and it has a lot less parameters so a lot less. So all of these are my parameters which I want to train, right? All these weights, and there are so many weights. So even for this small network, if you see, so the number of connections here is, so every thing is going into everything else. So here there are 8 uh, nodes. Here there are 6 nodes, right? So the total number of connections here is what is like 56, right? Sorry, 8 into 6 is how much? 8 into 6,
48.
yeah, 48, sorry. So yeah, there are 48 connections here, and then 8 into 4 connections, 32 more connections here. So even for this very small network, there are a total of 48 plus 32 parameters which I have to train, right? So this can get very out of hand very fast. Okay, so like usually, so for an image, so I want to pass an entire image like this, right? And an image is a collection of pixels, right? And say a good quality image will have 1000 by 1000 pixels. So 1000 by 1000 means there are what, 10 to the 6 inputs only, and then I have to map them to all of these some number of neurons in the hidden layer, and then there'll probably be multiple hidden layers. Then there'll be an output layer. So you can imagine there's an absurd amount of connections, and like training this sort of huge network, first of all it requires a lot of data, and it requires a lot of computation time. But if I use a CNN, if I use a convolution network, and I use a convolution operation, then the number of these weights reduces vastly, like it reduces like by orders of magnitude basically. So it is much easier and much faster to train, and it is like it's got like better accuracy than a simple like feed forward network like this. So that's why, I mean, it has all the good properties, so it is used for images. I mean, it can obviously also be used for other problems, not just working with images and classifying images, but it is most powerful when it is working with images, because like that is when it becomes the fastest. Like I mean, working with images is preferred with this kind of network. So there are other
Okay.
kinds of networks as
So
well.
the you can
So I think the professor talked about recurrent neural networks also, right? Little bit. So RNNs, recurrent neural networks, which have small loops in the. So this neuron will have a loop inside itself. Okay, so it will perform another computation inside only. So those kinds of networks are very good for working with text. Okay, so any text based work which you have to do. So say like translation, like say something like how something like Google Translate works. Okay, so translation, speech to text. So whatever you're saying, it is converting into text. Then yeah, so for applications like this, recurrent neural networks are preferred because they work best. Like I mean, working with text is best with a recurrent neural network, or yeah, some advancement of a recurrent neural network. So yeah. There are so as you get more and more into like machine learning, so there are some specific networks which serve specific kinds of networks which work best with specific kinds of data, right? So we have the main things we want to work on right now are images and text, right? And yeah, I mean text is connected to speech. So images, text, and speech. So images are usually handled by convolutional networks, and text and speech is handled by recurrent neural networks currently. So yeah, any more questions? So let's try to-
How many hidden layers would be there? How to know that?
That is something which is called hyperparameter. So it is not fixed. It varies from problem to problem. Usually, I mean, if I have less data, if I am trying to make a small network, I won't start with say 10 hidden layers or something like that. I will start with maybe one or two hidden layers, and then try to build up from there. So I might add a hidden layer in between and see if my accuracy of predictions is going up. So if it is going up, I will choose to keep it. Otherwise, I will. I mean, if it's the same or if it's becoming less, obviously I will delete that hidden layer. If it's and even if it remains the same, then I mean the accuracy remains the same, then I'll just delete it because it did not add any value and it just added complexity. So I will choose to delete it. There is no hard and fast rules or anything which you follow. So there are multiple hyperparameters like this. So you could choose the number of neurons also. So the number of neurons in the hidden layer is also not fixed. You can start off with any number you want, and yeah. So usually the only the number of neurons in the input and output layers are fixed, and everything else is variable. So how many layers you want to add, how many neurons you want to add in each layer, right? So everything else is variable, depends on the problem. uh, so if it's a small problem, I'll start off with small numbers. So say just one hidden layer with, so if I have six inputs like this, yeah, eight or 10 uh, things in the hidden layer make sense. Then my output layer has four neurons, so those 8 or 10 neurons in the hidden layer get pinned down to four. Yeah, that is how it works. Okay, anything else?
I think that's fine. Yes.
Okay, so if no one else has any questions, I think we can end the session for today. It's a little early, but okay. So yeah, see you guys again next week. So we'll meet again on Monday, and yeah, before that there are two more sessions by my fellow TAs. So yeah, you can ask any of your doubts there. So I think the session on Saturday, he will be discussing week 4 content there. So you could choose to ask your doubts there as well. And if not, yeah, I will also be discussing week 4 content on Monday, next Monday. So see you then. Yeah, thanks guys. Bye bye.